Good morning, all. Uh, Let us start the lecture number 3 for analysis and design of high-rise RCC buildings online course. The lecture 0, we started with the requirements of the approximate methods. And for a simple portal frame, we had seen how the SFT BMD is affected. Also, we had seen that how the position of zero moment is critical in the approximate moments and the approximate methods, and the approximate moments that we estimate with when we compare it with the software. And there's a direct procedure through graph in the book of Adrian Scarlett that I had shared with you. The second method is moment distribution method, in which we can estimate the 0 points using the triangles. And this another method would be the computational method in using the stiffness method or finite element analysis procedure. So stiffness method will give you the stiffness and bending moment diagram. So globally, when you are looking at the structure in a global respect, then stiffness method works. When you are looking at a local perspective, then the finite element analysis is used. Okay, so stiffness estimation for the building as a whole, you are using the stiffness methods. Now, lecture 0, we focused on the list of approximate methods. And lecture 1, we went to the behavior of the buildings from the reference of Dr. C.V.R. Murthy, in which the seismic behavior of buildings is explained in very detail. And I had asked you to at least go through the initial sections so that you understand that what is the requirement in seismic design. So still you have time because I have given you some literature in advance. It may give you 3 weeks to read. So after 3 weeks or 4 weeks, we are going into the main designs. So you should be aware about approximate methods. What are the principles in design? We will also go through in the codes. We will open the codes and go through the clauses for seismic design, right? But fundamentals has to be clear. That is why I have shared the literature with you. So by the end of the course, you should have at least understood what are the definitions, what are the parameters, because you should be able to answer on all these parameters. Until you don't understand, you will not be able to answer it. Yeah, so you have to understand all these aspects. So don't have to mug up, but you have to understand. So book will enable you with some things that many people ask that why the interview is not getting correct, or why I am not able to solve a problem. The reason is that you have not gone into the depth to solve the problem, right? And structural engineering is all about the depths, how much depth you are, if you understand the concept. That way you can solve a problem in multiple ways, because solution cannot be one. So if I tell you that this is the solution to this problem, you will stop, you know, growing, and you will say that this is the only solution available to this problem, until unless you understood what are the parameters that govern, and in what case, what should I do? Okay. So that is how a solution is provided, and that is only appreciated in the market, or let's say in the professional practice, as well as in research also. It is even more necessary to understand the parameters, right? So I'll again, we'll go to the approximate methods today for manual design. Okay. Hope the screen is visible to you. We are today on the third week of this course, which is lecture number 3. That means it is third week, and third week means it is 20 days in the course, and I expect you to at least read and understand the methods, because we have not gone beyond the principles and methods up till the 3 weeks. Okay, so you should be aware about these things, because later on, when we move on to the software, things will run fast and you will not be able to grasp what is happening in that particular scenario, right? So it is mandatory for you as well that within the week nobody is asking the questions, neither anybody is going through the methods properly. Okay. So query is not coming. That means either it is fully understood or it is not understood. Okay. So let us take a simple plan that I have shared with you for a 8-story building. Same type of plan I will make. So this previously also we had seen similar type of a arrangement. Or okay, no problem. So these are the column positions. All grids, the columns will be there. Okay. So all are columns, you consider that. Now I am taking one particular slab area, okay, within this, because I want to solve this building using the manual procedure. So let me make it more symmetric. So I can take the central bay. So all have mostly in their UG as well as PG would have solved a similar problem. Okay. So let's say this is the central frame that I am targeting to analyze. And I will name it the grid A, B, C, D, and E. And this will be 1. So it is 5 by 1, 2, 3, 4, 5. 5 by 5 grid is there. So in ETABS, when you enter the grid, it will be 5 by 5. Or similar to what I have shared with you, you can use the same. And now this is the frame of interest for me. Right. So these columns, beams are of interest for me to analyze in 2D. So in 2D, I can only solve this particular frame. However, as per the soft requirement of the code, okay, you have to do 3D analysis only for the building. So whatever 2D analysis you are doing is only for reference comparison and preliminary design. However, when you are doing for any building, as per the IS 1893, it is clearly mentioned to do three-dimensional analysis of the building. So you have to do three-dimensional analysis only. For that purpose, you will use the software. So when you see how much area is participating for this frame, I will hatch that portion. So this full area will not be participating. Half of the area on top, half of the area on bottom will come into picture. So half area above slab and half area below the slab. Okay. So this is the effective width you are going to consider for estimation of the load for this particular frame. Now, if you look into this arrangement and let me take this particular slab, which I am double hatching. for analysis, because first what will you do for this particular frame is the gravity load. So what are the gravity loads? First we have to list it out. Gravity loads, what loads are required. So in gravity load, we are using IS 875 part 1, that is for dead load and super dead load, and IS 875 part 2 for live load. Okay. So both you should have referred what type of building it is, the type of the loading changes. If it is assembly building, institutional building, or it is a residential building. Based on that, the load criteria have been given. For different materials, the dead loads are given. Density is mentioned. Okay. So that way, you have to refer those codes, and from that you have to provide those loads. So in gravity load, now you know there is a dead load, then there is super dead load, and there is live load. And other loads like there is a water tank load, and other would be your landscape would be landscape would be separate from this, but it is part of super dead load only, but landscape I am mentioning separately. Then there is water tank, then there is landscape, and if any machine is there, so machine load you have to consider. And there is another load that we take for a different type of arrangement, that would be for the HVAC oblique your false ceiling. Okay. And other would be your it's elevator. So all these things we give under the super dead load, and some part if some part is we have to take as live load, we take it, but this mostly comes under the super dead load. Right. So elevator is a live load or a dead load? That is the question. Has anybody seen the IS code? Elevator load is live load or whether it is a dead load? So can anybody say on that?
Sir, by
And
elevator you are referring to lift load.
yeah.
That's called a live load.
Live load, right? So, so HVAC and false ceiling, they can be under super dead load. Okay. But elevator is a live load. So category of live load is like this. So water tank load is a live load or a dead load?
Actually, sir, for dead load only. Because in live load, we have to reduce the, like for lumping, we reduce that 25% or 50%. So we mostly consider it under dead load.
So this is all under super dead load. So actually dead load we in ETABS we are taking as a self weight mostly. Okay, so self weight and other loads we can separate, so that we have to change something, then it is not affected. So self weight will come under a dead load, and super dead load you can take other loads that may have a variation later on. You may be deleting also, no problem. So what happens that again and again you will have to update your dead load, because if in dead load you define 5 items, then those 5 items again you will have to edit. You will not be able to delete. Otherwise, you will have to open the editor file like in stat. In ETABS also there is an editor file. You can delete from that and then save it. But to model and make it simpler, we separate it out. Super dead load and dead load. And live load also, why I have mentioned separately, because this is also a variable item, so you can keep it separate. So what can be variable, like machine, water tank, landscape, floor finish. So the super dead load, let's say if I write as floor finish also, so this will be a super dead load. And these are also super dead loads. So machine is a live load or a dead load? Machine loading, any machine is kept in the floor, whether it is a live load or whether it is a dead load.
Live load.
So why it is live load? Why not dead load?
It will also have a dynamic weight, sir, also, the machine.
Dynamic weight, let's say it is a, this, it is not a dynamic machine,
Okay.
then will you take it as a live load or whether take it as a dead load?
Then dead load.
So means it is not reducible, right? Right? During
Yeah,
like
equipment will not reduce.
25%, 50%. So equipment will remain at that particular place. So machine or equipment, they will be categorized under super dead load, right? The weight of the machine, that is not going to reduce along the height of the building, neither during evacuation also, neither it is going to change its position. So we can take under super dead load. And service condition also, it is critical to check if any machine is there on the floor. So that way, this all, if we list down all these loads, they are all gravity loads. Depends on case to case, building to building, what is the scenario. You have to first categorize it, list it, and then you have to create the load cases. Right now we are discussing regarding dead load, super dead load, and live load in simple cases, simple understanding. Okay. Now in dead load, I have taken a self weight. Super dead load, I have taken as floor finish, and live load, as it is a residential building, I have taken 3 kilonewton per meter square, let's say. And there will be now water tank load that will come, but in routine floors, it is not the case. At the floor that is for use for evacuation. Okay, for firefighting, tanks are also there on that floor, so that whenever the water tank is on that floor, it is mostly at least 1.5 meter height or 1 meter height, that way. So 1.5 meter height, if I am taking the height of the water tank, multiply by 10 kilonewton per meter cube density, I will get 15 kilonewton per meter square as the UDL. So this is the tank load, or I can say fire water tank at any floor where the evacuation or the firefighting is going to happen. Every 8th floor you have to give a stilt floor for this particular purpose in the buildings as per the requirements of local bylaws. So at that particular floor, so small area also will have the water tank load. So right now we are not going into that also, but whatever the loads are coming, you should know at what floor what loading is going to come. And on terrace, there is OHT, overhead water tank. So that portion, overhead water tank, similarly height of the water multiply by density, you get kilonewton per meter square area load, and self weight of the members and the wall has to be provided. Then we can take all those things, right? So all these are area loads. What I am writing, these two are area loads. Now, what can be the other super dead load is of the walls, main wall and partition wall. Okay. So right now, when we take AAC, we take 10 kilonewton per meter cube as density along with plaster, or 20 kilonewton per meter cube density if it is a brick wall. But bricks are now less they are used. AAC blocks, lightweight blocks are mostly used. So this is the density for the walls, maybe interior or exterior. Now exterior wall, it may range from 200 mm to 300 mm based on the height. If it is a 4-meter high story or whether it is a 3-meter high story, the thickness of the wall will vary accordingly. Now for this, we are taking 230 as the main wall. Okay, 1.5 brick walls. So these are the main walls. Partition walls 150 mm, and here also the partition wall can be let's say generally it is 115, or you can say here also you can take as 125 or 150 also. 150 difficult to achieve in this wall. So 9-inch is the this one, what we say that what is the width of the RCC? It is red brick. Do you remember? 190 is the bigger dimension. What is the shorter dimension? Or any other dimension you remember? This is one dimension I have written, 190.
9 by 9, sir.
90 by 90. What is 9 by 9?
I mentioned centimeter actually.
So 90 mm, 90 by 90 by 190. There are other sizes also of the brick that are used. So based on that, your wall. So this is 90. Now, what will be the thickness of the partition wall in that particular case? So if a single brick wall is there, width is 90, the plaster 20 mm plus 12 mm, it will be 32 added. Okay, 9 and 3, 125, right? Round about 125 mm is you will get for partition wall. Right, so that way you have to take the partition wall, main wall, whatever the AAC block or red brick is there. So once you get the thickness, once you get the density, and again you have to get the height of the wall. So from that you will get the UDL load. That UDL load will be density into your thickness into your height. That way you will apply this UDL on the beam. Generally, we don't put directly on the slabs, but if something is coming on the slab directly, then you have to also apply on the slab. But mostly we don't recommend to put directly on the slab. Another is related to your glass, or you can say window frames, right? So how do you take care of the load coming from the window frames? So how do you take that load? So these are just basic things. I'm just going through that. So wall load. Now another is the window frames. How do you take care of the window frames? What loading do you apply? Or you apply the same loading as the wall and then, or how do you do?
Same as the wall actually, so we usually do not consider window frames. And for small scale buildings and all, we do the same.
Yeah. So until the frame is very heavy, then the wall, because see, we are using lightweight blocks now. So previously it was a brick. So we were taking the same. density or weight. However, aluminum is also light, so that's why the loads are lesser. However, if the frame is heavy, for those frames, you should estimate separately. So if they are heavier, than wall, then consider separately. Okay, so this would be the UDL load, that is uniformly distributed load onto the beam. And surely there will be stilt floor in which you have to take the firefighting water tank. So if I take as water tank, it will be again area load. It will be density of water multiplied by height. So 10 into 1.5, 10 into 2, whatever the height is there, you have to apply that as the area load. And there will be again walls. So water tank is area of the water and plus UDL for walls. So this is all under your super dead load, right? So what loads to estimate? You should know that first. So you should write. So whenever you are doing the calculation, first step you will write as gravity loads. You will list down what are the gravity loads I am going to consider. So the step 1 is to draw the geometry. Step 2, enlist all the loads with category. Then step 3 is to estimate. Estimate the loads and their reaction on the frame elements. Right? That would be the step 3. Now we are on the step 3 that we are going to discuss. So whatever I have highlighted, I'll take it to the next page. So if I am onto a particular floor plan, or I'm taking just one particular slab, and I will give this B1, B2, B3, and B4, and this is a two-way slab, right? So the load distribution will be trapezoidal load onto B2 and B4, and triangular load on B1 and B3. So this direction would be LX. This direction would be LY, where LY is the longer direction and LX is the shorter direction, right? And there is a factor called beta, which is equals to Ly upon Lx. So this sketches I have shared it because it is very long known. Nothing is hidden how this load is estimated. So this way that derivation is given. So in this particular case, we have to draw two beams. One is the smaller beam, which is let's say B1 oblique B3, because load is going to be the same. So there will be a triangular load distribution here. Then there is a longer beam, which is B2 oblique B4, which will have trapezoidal load. And if let me open that what I have shared. So intensity of load is going to be the same. Q into Lx by 3, Q into Lx by 2. So many different places, different are shown. Okay, I have also shared you 2 sketches for that. However, what I take is in this particular case, it is given in the book of Shah and Karve also that intensity of the triangular load is Q into Lx by 3. Q is the intensity of load. Right, which is kilonewton per meter square. So whatever the kilonewton per meter square load you have applied, now you are going to distribute it. So we are looking at the load distribution onto the floor for area loads. Okay, so this is the area load. And whatever will be the length Lx, you divide by 3 into Q, you will get this particular load intensity. And now you know that you will have to calculate based on the triangle, whatever the CG is there, based on that, how to estimate this your force. And bending moment you need to estimate. So in this particular case, what is the value of the force? How will you estimate a force from this intensity load? So whatever the uniformly varying load UVL multiplied by the area, you will get the load, right? So area of the triangle multiplied by uniformly varying load, that is 2 into Lx by 3 multiplied by 1 by 2 into what we say base into height, right? So what is the base? Base is Lx and height is your Q into Lx by 3. Is this correct or what? What should be the value for this? So what is the meaning of this area and what is this UVL and how will you get this force? So any UVL, something like this is there, right? In which there is some Q intensity is given. Let's say it is X kilonewton per meter load. And this is the length. What do you take as the load is at this particular CG. Okay. Now this load is estimated from the area of this particular graph. So 1 by 2 into base. What is the base? Let's say L into X, right? That will be the load, right? Something like this. What should be the answer for this? Anyone? So UVL area or UVL into area, what should be there? So your CG is coming at this particular point. Anyone? Hello? Anyone?
Yes, sir.
Yeah, so what is to be written here? Basic mechanics, once we go into that, this particular triangle that I have drawn is right or whether it is wrong?
So from left side, we take 2/3 of that CG.
No, 2/3, 1/3, why will we take? If I have to take a moment, then I will take, but I want force, not the moment. What is the force from UVL? How do we get a force from UVL?
That half into base into height is correct, sir. Actually, UL of the area has to be put up. That's it. Not UL into area, sir.
So UVL area. So
Yes,
only
sir, UL
area
of
we
the-
have to take.
Yes,
So
sir.
when we are doing with UDL, okay, this is X kilonewton per meter. We estimate a force, right? That is X into L, right?
Yes,
Which
sir.
will give us the force. So area of this UVL, basically, if I draw it similar to this, we are taking the area of this, right? Whole area, X into L. That is the load. So I will draw similar for this also. This way. This is also X kilonewton per meter. So this area is equals to 1/2 into X into your L. This area is equals to X into L. So is this equal to force or not? Right?
Yes, sir.
Now, if I have to take the moment for this, that is a separate calculation. So in this also, if I apply the same logic, is 1/2 into Q into Lx by 3. Height into base is your Lx. So that will be Q into Lx square by 6, right? So force applied directly in the center. Now there is another into this particular case that there is a equivalent UDL. So this was a UVL that we did the analysis. Now what is the if I want to draw equivalent UDL for this, I don't want to make a triangle. I want to convert it into a equivalent UDL. This is even more approximate, but you can convert this triangular load into a equivalent UDL load. So what will be, so that also I have shared in the group. This will be 2/3 W, or let's say Q, into Lx by 2. So in that particular case, what they have considered, this Q into Lx by 3, they have not considered. They have considered everything is Q into Lx by 2. So in that particular case, it will become Q into Lx by 2 into 2 by 3 as equivalent UDL. But once you take Q into Lx by 3, this also can be 3. But both expressions are available like Lx by 2, Lx by 3. I follow Lx by 3 and I don't take equivalent UDL. I prefer to take directly from this formula. Okay. But there is a formula for equivalent UDL also if somebody asks you. And continuing with this particular UVL, you will get the bending moment. So bending moment will be how much? So for this particular diagram, what will be the bending moment? So let's assume it is a fixed beam. So what will be the bending moment for this? Anyone? So I don't think you have
Q
gone
into
through
X square
the
plus
yeah
into L by 2, sir.
into L by 2. Yeah, that
Yes.
is also possible. Another way is also there, but we will see that separately. But this is okay. Q into Lx square by 6, that is in the center, that is multiplied with Lx by 2. So the Q into Lx cube by 12, right? This is what you are saying, right? So is this we solve
Yes, sir.
a fixed beam? Means you understood the problem, right? It is a fixed beam problem to be solved, not a simply supported beam. However, for any beam, so let me say that this is the fixed beam and this is the W at the center. What will be the bending moment diagram? You already know it will be like this. All straight lines. This will be the right directly at this point. The maximum will come. So this is negative and this is positive. However, when we are solving for UVL, your bending moment diagram is you know something like this is parabolic. The cubic. So my the question is whether this bending moment diagram is parabolic or whether it is cubic. In case of UVL, this is the point load.
It is cubic, sir.
Cubic, right?
Yes, sir.
So bending moment diagram is cubic curve for this UVL. When it is UDL, then it is parabolic curve. Okay, and shear flow diagram is cubic or parabolic for UVL?
Parabolic, sir.
Parabolic.
Parabolic, yeah. So this is the bending moment diagram we are drawing. So I should write that BMD. So that way it is cubic. Now the difference between the two you can see. So how will you estimate? Will you do like this or how will you estimate the load? So for a point load, we remember that it was written WL square by 12 when there was UDL. Okay, not point load. Point load is WL by how much?
WL by 8.
WL by 8, WL by 4, WL by 8, right? This way. Is it correct or not? So for
No,
you,
sir. The center span
so
should have lesser moment. The end spans, end moment should be more actually. Here it is the other way around.
what should be the moment then?
WL by 4 on the fixed ends and WL by 8, WL by 8 and WL by 8, sir. All four, all three.
Actually, the moment
Because,
starts from this point.
yes, sir.
So this portion of WL by 8 is not acting. That we are substituting as negative moment, and this much portion is considered as positive moment. So for a simply supported beam, this triangle with dotted will come, and this much portion WL by 8 was uniform. So when we overlap this uniform area with this triangle, okay, you get the final bending moment diagram, as you can see. So I think WL by 4 is correct.
Sir, for a
So
fixed beam, will the
yeah,
negative moment be more or a span moment be more, sir, actually? As per the general logic, I feel that the fixed end moment should be more than the span moments. WL by 4 concept, WL by 4 indicates that, the center span moment is more in comparison to the negative moments. Is it right, sir, that way?
WL by 8, sorry, WL by 4. WL by 4 is the right answer, even if you refer any book also. WL by 8 we have to check. However, WL by 4 is the right answer. Reference I am also searching from where I can share it with you. However, in SP16, these are all mentioned. If you refer SP16 at the back end, so this WL by 4 is correct. And in this also, if you remember that this will come as the fixed moment. So fixed moment MA, fixed moment MB. This is how we get in the textbooks. And this is WL
Sir,
by 4.
Sir, for point load, MA, MB, and the center span moment will all be WL by 8, sir.
WL by 8.
Yes, sir, all be WL by
For
8.
fixed beam.
Fixed beam, right?
Yes.
Yes, yes, sir.
So why I have written WL by 4? For simply supported, it is WL by 4, right? This triangle. From that, this is WL by 8 that I had written previously, or like this. This overlapping diagram, this much has to be minus. So WL by 4 minus WL by 8 will be equal to WL by 4. Sorry, WL by 8. Right?
Correct.
Correct. So this way, this WL by 4, if you see, that means this much has to be deducted from it. And this WL by, L by 8 will come. So effective, this much will be the bending moment diagram. Negative and positive, that way. Write it in simple is WL by 8. When it is UDL, it is WL square by 24 in center, WL square by 12 at the ends, right? So if I make it as a UDL and a fixed beam, first it was WL square by 8, right? And at this particular junction, fixed beam is there. Now this is WL square by 12. So WL square by 8 minus WL square by 12. So how much is the base? Has to be 24. So 8
Yes, sir.
4s are 8, 3 are 24 and 2. So 3 minus 2 is 1. So WL square by 24 will be the answer. Right. So for the UDL, it is WL square by 24 and WL square by 12. Similar approach is for this. So WL by 4 is written, WL by 8 is the fixed moment, minus from that is WL by 8. Okay. And this cubic curve, now my question was, how will you draw the bending moment? And based on that, you have to estimate the bending moment, right? If you are taking as a point load into L by 2, so will you get the same bending moment or not? So I basically want a graph to be like this for bending moment, not like this. So how will you get it? So is this expression looking cubic to you, right? So this is okay. This is looking parabolic to you. This is okay, right? So it is matching, right? What I'm trying to say to you. Q into Lx by 3 is cubic curve, right? And your force is the parabolic curve. So that looks okay. So from that you can understand whether we are going in the right direction or not. Okay. So this fundamentals I just wanted to cover for fixed beam and how the moment and shear force are estimated. For that we had mentioned it in the side. So the cubic curve and your parabolic curve you can see from the equations that are written here. And this equivalent UDL is the second choice from which you can also estimate the bending moment. So if it is a equivalent bending moment, then how much it will be the answer? It is 2 by 3 of Q into Lx by 2 into Lx. That will be Q into Lx by 3, right? So that will be your, if you are using equivalent UDL, you will get a bending moment Q into Lx by 3, which is quite different, right? From this to this. Lx square, sorry. Q into Lx square by 3. So you can see the difference. It is a UDL, whether it is a cubic curve and this is parabolic curve. So this is what I will mostly prefer to evaluate. However, there are both methods available, converting UVL into equivalent UDL or using the UVL. So UVL and this is equivalent UDL. So I hope this is clear how we are taking for the this is a shorter span. So I will take as a short span load distribution in which the length is Lx. Now other would be trapezoidal loading, which is a long span load distribution. this is your Ly, and this is Ly minus Lx. How this Ly minus Lx is coming, that if this is the span, and this way the load distribution is there, this is 45 degree, and this is Lx, this is Ly. This dotted that I am drawing, that is remaining distance, this distance, and this distance. This is 45 degree triangle, right? So whatever is the length in this direction, similar length will come in this direction. So this length is Lx by 2, and hence this length is also Lx by 2. So if you add this plus this, it will become Lx. Okay. So Lx by 2 plus Lx by 2. So that will become Lx. So that's why this top portion, the length is given Ly minus Lx. Right. What is the intensity of load in this? It is Q into Lx by 2, 1 minus 1 upon 2 beta. Okay. So this is the intensity, and beta is Ly by Lx. So from that, you have to estimate the loading, which is triangle and rectangle combined. This is for beam B4 oblique B2, which is a longer span load distribution. So similarly, you have to estimate the force for this particular arrangement. So how to estimate the floor for this? So your Q into Lx by 2 into 1 minus Lx upon Ly, 2 Ly. And this is the intensity of the UDL. So what I am taking in this are two parts. One is the UDL, in which there is Ly minus Lx is the length. Okay. So this is for that portion. So this I have to multiply by Ly minus Lx. Now I will take for this triangle, remaining triangle. So I have to add the intensity is Q into Lx by 2, 1 minus Lx upon 2 Ly into 1 by 2 into, now Ly minus Lx has happened at this particular portion. So I had told you this is Lx by 2, right? This much distance. So Ly minus Lx, if you are taking, so Ly minus Lx, what will be the length of this portion? The question is, what is the length of this area? This UVL. How do you get this length? So it will be something like total is Ly. From that, you are deducting Ly minus Lx. Okay. And that whole has to be divided by 2. So this will be Lx by 2, right? As I had explained you previously. So this is Lx by 2. Is it clear? So total is Ly minus Lx divided by 2. So Lx by 2 will be the answer. Yeah, somebody was saying. So this will be Lx by 2. Correct? And we have to multiply it by 2. So these triangle 1, triangle 2, and third is the center portion. So all three parts we have added to find the force. Now you have found the force. Now you have to also estimate the moment for this. Similarly, you have to go with the CG, multiply by L by 2. In the center, for triangles, you have to take 2 by 3 or 1 by 3. That way you have to consider for that particular case. Right? So is the load distribution and calculation of the force and bending moment clear to you? Then we can move to the next step. So this is for two-way slabs. So moving on ahead. So once you have done for this particular any one frame, okay, you have estimated on the beam. So I will let's say take another part also. So if it is a one-way slab, okay. So in that case, equal load gets distributed on B1, B2, if this is B3, B4. So there is no shorter span or there is no longer span. So major bending will happen in the LX direction only. So bending direction is this. So main bending. So bottom reinforcement has to be in this particular direction. Like if this is the bending that is happening, so reinforcement will be like this. This will be the main reinforcement on one-way slab. And this will be the this direction would be the secondary reinforcement, which may be higher distance. We call it distribution steel. And this bending will be like this. And there is a distribution steel. Okay. So I hope the reinforcement distribution is clear to you. So main bending is in minor direction, lesser direction, and bottom reinforcement has to come first in that direction. So this will be the bottom reinforcement you will be having. This will be the above one. So first you will place the one reinforcement which is vertical. Above this vertical reinforcement, you will put the reinforcement number 2, which is distribution steels in horizontal direction. So that is how it has to be provided. If we see a slab which is one-way slab, so if this is the bottom reinforcement, okay, so this is your 1, and above that this reinforcement near shown. Okay, so this will be the 2 reinforcement. So is it correct or not? Is this correctly made or not made?
Correct, sir.
Correct. So if this is LX, then it is correct. Not a span. So that way, that is the detailing part, how the bending is taking place. That is also critical. Okay. Where is the main bending happening in one-way slab? Now the load is equally distributed on B4 and B3. So we have to make a beam, give it B3, B4, which is a shorter span, but 100% load distribution on shorter span. And this will be how much? So it will be Q into Lx by 2. So these reactions you will get, this is a uh, fixed beam. I think it on here. Okay, so this way you will get the bending moment and shear force from this particular beam. So these reactions are critical. Once you get these loads, which are the gravity loads, which is dead load, super dead load, and live load. They may be the area load, they may be UDL load, they may be UVL load. Once you are estimating all the loads and putting onto the beam, okay, then we can apply beam reaction method to obtain the final result, case 1. That is a very simple and also approximate method. Another is we can go for the moment distribution method to solve this entire bay. So you can choose your method. Also, I would suggest you can do a comparative by beam reaction method and moment distribution method, that which is giving you better result, right? So this is the load distribution when it is a one-way slab. So for this, the force and shear force, or force and bending moment, you have to estimate. So it will be Q into Lx square by 4. No, it is Q into Lx square by 2. And bending moment will be your, let's say, how much will be the bending moment for this? So should it be WL square by 24 in the center? Is it like this or what? So is this right or not? It is bending moment, directly the value is there. Or if I go something like this, Q into Lx by 2 into Lx, this is the force, into Lx by 2. Then this answer would be Q into Lx cube by 4. What should be taken? So which is correct from these two? Anyone? These are very simple cases we are discussing. So can anybody say that which is correct? So this is the central moment that I have written. Now if I make it for the ends, this is for the ends bending moment. So q into Lx by 2 into Lx square divided by 12, just the half of it, 2 into Lx cube by 24. This will be at the end. So not in these two, which is the correct bending moment. This is the mid. So what is the bending moment I should be using? That is the question.
Sir, this is one-way slab, right?
Yeah.
If it is one-way slab, then and the ends are fixed, then this one is right. You know, the one which we have written in the figure, WL square by 12 and WL square by 24 in the middle and WL square by 12 at the ends.
So what logic we were using previously is the same we are using here. We are converting this UDL, right, into point load and then multiplying by L by 2. Then why it is not giving me this answer? Same answer. So if this is the load, Q into Lx by 2 into Lx, right, and we divide it by 2, we get the reactions. Now in the reaction, if I multiply by Lx by 2, then also it will become 4 to the 8 that way, right? Now in this again, what I have to do, Q into Lx cube by 8 minus Q into Lx by 2 multiplied by Lx by 2. That will give me the force multiplied by Lx by 4. So Q into Lx cube divided by how much? 16. We try. What is happening here? Multiplied by 2 I have to do, right? So 8 2 is 16. And this will become Q into Lx cube by 16. Let's say, my only thing is it should come WL cube by 24, not anything less than that, right? So this is not the correct way to estimate it. First find the reaction. From the reaction you multiply up to the center, and whatever the load is applied, that also you take to the center and then estimate the central bending moment. So that way it will work correctly. Now how do I get this WL square by 12? From where I have got this moment? How I got this moment WL square by 12? In a fixed beam, we have got WS by L square by 12. From where we have estimated that? So that is why I always ask people to read a textbook with some purpose. Okay, so it helps you to, at least uh, apply those logic into a problem when you are don't have that direct solution is not available. Today we have available direct solution, but in some cases the it is not available. If you don't remember the derivatives, you will not be able to uh, convince your own self. So this way, WL square by 24, that is the mid bending moment. WL square by, sorry, 48. 24 is the end bending moment you have estimated for this beam, which is B3, B4. Okay, so this force, what I had written, Q into Lx by 2 into Lx. That is the force. And reaction will be divided by this 2. You will get the reactions. So what you basically require is, let's say RA, RB, then MA and MB. Okay, this is how it is for any particular slab. So one-way slab, two-way slab, we have seen how the load distribution takes place. Now the next part is related to, again I'll go to the plan that I had shown. Now in this particular plan, I had focused on this particular frame, right, that I have marked as arrow. So let's say this is my B1, this is B2, this is B3, and this is B4. So whatever the trapezoidal load is going to come, all trapezoidal load, let's say if two ways in this particular arrangement. So if this is Ly and this is Lx, okay, then this is the arrangement. Right? So this much is the load that is coming onto this particular frame. So this beam will have these gravity loads coming from it. So all these loads are the area loads that is coming onto it. Okay, this area loads is live load or self weight of the slab. Self weight of the this area load is floor finish. Then live load is also there. If water tank load is there, that also to be considered in area load. So this what we have seen is for the area loads distribution. So once those area loads are estimated, so area loads are estimated, then distributed on beams, and from beams, what we say that you can apply the approximate methods analysis for area loads. Now, when it is UDL, you estimate the UDL load, apply on beams, and then approximate analysis. So you have to total all these loads, right? That is coming onto the beam. So you have estimated loads. Which is the floor element that is taking the loads are the beams. So you have to estimate all loads coming onto the frame element, that is the beam, and then you have to transfer it to the columns and from columns to the footing. So that is called the beam reaction method. Okay. So one is the beam reaction method. And this is the most common method that is used. So whatever the load you have estimated on a beam, that is the UDL. Also point loads may also be there that are to be estimated. Okay. I'll draw reactions with different color to focus on what is the requirement. So these forces are the required product that is to be used in the beam reaction method. So these reactions will be transferred to the columns. So in gravity load, there is no stiffness difference in the column, and hence we are dividing it appropriately. However, you also know that in which direction you have to consider the loads, you have to take it that way. So in one direction, I had marked this blue, a strip for the estimation of the loads. So this blue strip is in this direction. That means these loads are estimated. The strip can be in the other direction also. Okay. So you have to select the direction of the strip for estimating the load. I hope I am clear on that particular case. So one-way distribution, two-way distribution, how it is going to be, how you estimated the strip. Now reactions are transferred to columns, then from columns to footing. And that is the base reaction. So hierarchy is like this. This is the slab that we had considered. Floor we had considered. We had beams below these floors. Okay. And we have taken the reaction for all the beams that are coming, including the moments also. You can consider all these moments that are available. Right? So all these moment and reaction we have taken to the beam. And from beam we have transferred it to the columns. That is single column which is taking two loads. This is the way. So this is this direction, so direction becomes opposite. And at the bottom, you will get again in the opposite direction. Right? And then it goes to the footing, and in the reverse order, it will go to the footing, and the footing will take this particular reaction like this. from the bottom. So hierarchy is like this is the slab loads including self weight. Then these are the beams are transferred to the beams plus self weight. So beam self weight plus slab loads. Then that is transferred to the column. So column self weight plus beam. Okay, that includes everything. Now here it goes to reaction. So everything is totaled here in the reaction part. So this is like cumulative estimation of the load till this point, which will be transferred here. So it will be self weight of footing plus the column. So everything above included. So that way you will get the reactions in this particular order. Is it correct or anything I have missed? Right? So what we have to do is we have to now draw a particular frame. That I had shown as arrow. Okay. Now we have to plot number of stories. So it is a 4-story building. So first you have to estimate what? You have to estimate the gravity loads coming onto these beams, which will be higher or it may be lower, depends upon the case. Whatever the point loads are coming, wall load, glass load, other loads, whatever are coming, you have to put it here. And from that point, top roof level point, you have to travel downwards. So if I give this as B1, B2, B3, and B4, you have to find the reactions and you have to transfer it to columns. Then at this level, B5, B6, B7, B8, and 10, 11, 12, 13, 14. Now there are 16 beams that you have to consider, and cumulative wise, you have to keep on transferring the reactions up to the footing. Right, so you will get a reaction at the bottom. So any doubt in this particular method? Anybody has a doubt to estimate how to estimate the loads, area loads, UDL load, and point load, and how to transfer these loads? So any query in this particular case? Any query? Okay, so we'll beam reaction method will close on this part. I'll now open what I had shared with you in the approximate method. Okay, this I had shared with you, in which there was a substitute frame method that was shown here. So here the moment distribution method is given in this literature. So this is what has to be followed. So mostly this is the method which is most commonly also employed, which is Carney's method or moment distribution method. So substitute frame method is necessary to estimate the maximum and minimum loads coming onto the floor. So positive maximum, negative maximum, how it is going to occur. So substitute frame method is needed. Now, second is the portal method is also given in detail. Everything is there. However, portal method has the assumption that so I had shown you book of Adrian Scarlett, in which the assumption that bending moment is going to be in the center. This is the routine portal method assumption. However, in the book of Scarlett, this point of zero moment, ZMP, is to be estimated from the graphs. And these graphs are dependent upon the stiffness of the beams and columns. So it can be either at this point, or it can be either at this point, or it may be a total cantilever that the bending moment point, 0 point is going above. So this is totally cantilever action in a floor. So these two methods, if you are using portal method and you want to improve it, you have to use these graphs and stiffness of beams and columns to estimate correct point of bending moment. However, if you are not using the portal method, then you are using moment distribution method or the Carney's method. So that is what we are seeing in this. So it is clearly mentioned in this reference. In any reference that you will see for substitute frame method, you would have seen previously also. So we are taking this half story from top, half story from bottom, and representing here. So here they have represented this particular floor. Okay, in which it is let's say they have taken full story. Okay, so this total this much story they have considered to analyze. Okay, so this has been drawn here to evaluate the this moment distribution method, how to apply and what is the bending moment maximum minimum values. The cases are to be demonstrated. So this you can see A, B, C, D, E, F. Now they have not marked anything A, B, C, D, E, F, but that is for our assumption that so if you see in this particular case, how will be the bending moment diagram? So if this is a fixed support in the centers, it is fixed, and exterior supports are pinned. Okay, in that particular case, the bending moment diagram will be something like this. Is zero at the ends. Now, if I want to have this maximum hogging bending moment, then what should be done? So in this particular diagram, you can see these two loading, which is a live load. Okay, so this load is the self weight. that cannot vary. So that is a UDL in all the spans you have to apply. This is the live load, which can be varied to find out the maximum hogging bending moment. So once you place live load only in these two spans, you don't apply live load in other spans. So what will happen? This floor will deflect more, right? Because of the higher load, and hence overall the hogging moment will increase. So negative moment, positive moment, negative moment. So that way in the full frame, the negative moment will increase, which will create higher hogging effect. So that's why that is higher negative bending moment can be obtained when two live loads are in continuous span. So this is continuous span 1, 2. Then this will give highest bending moment in negative case. Negative bending moment. Now maximum sagging bending moment. Again, if we draw, this will be bending more. Okay. And this will be bending less. This will be bending more that way. So this will give higher bending effect because two spans are bending and this is having less impact in bending. So this will give us higher positive bending moment. That's why it is called maximum sagging moment. So this is the alternate span. So this is the same or near span. The live loads are applied in alternate span. If the live loads are applied, then it gives the maximum sagging bending moment. So maximum positive moment, maximum negative moment, we can estimate by providing this type of arrangement of the live load, right? So that is in substitute frame method. We are going into this particular way. So maximum sagging, you started from the first alternate span have the live load. Here continuous span have the live load in the center. So that will create higher hogging at the two other spans nearby to it, outside span. That's why in the center they have applied the continuous tool. For column B. So this is the case you can see in center CD. So in the beam arrangement, say, so right now what we saw the two cases, that is for the center span CD to have the highest sagging, to have the highest hogging bending moment, CD and DE. So this much for negative and this is positive. Now if I want at other joints also maximum positive and negative, then what I have to do, so what will happen here, this will have higher bending. Okay, so higher bending, I think so. We will get moment like this and something like this. So what it is showing, arrangement of loads for maximum bending moment in a column at B. So at B, there is a negative bending moment, right? Always not a positive bending moment. So highest negative moment you want at B, then you apply on that span, either interior or exterior, both in the case, the B will have the bending moment in that particular order. So they have given a graph in which you can see that they have given a table in which they have explained the various conditions that everyone has to apply, like maximum hogging moment at D. So live load apply at DE and CD. That means continuous two spans. You apply the bending moment. You will get the maximum hogging in the center. Maximum sagging moment at B. Apply the live load at BC and DE. These are the alternate spans for sagging. Now minimum sagging moment at center of the CD. So what is the minimum sagging and what is the maximum sagging? So minimum sagging you will apply at AB, starting alternate span CD and EF. Then there is minimum sagging moment at the center. Now maximum axial force in a column at D, that is maximum shear in beam CD and DE. So CD and DE you have to apply. So CD and DE, same case, continuous two spans for column maximum shear. Now maximum moment in column at B. So one is the case we have estimated for beams. One is for the columns. Okay. So two cases we have to create. One is for beams, one is for the columns. So this is how it has been shown. So for both cases, you have to refer. For columns, what is the case to be taken? For beams, what is the case to be taken? For highest bending moment and shear condition. Right. So this I had shared, I think last week before that maybe. But if you have gone through that or not, I don't exactly remember. But these things have to be considered while application of the load. This is very critical because after this only the moment distribution method can take place, or this next analysis can take place. So what are the steps for analysis? Select a substitute frame by taking the floor beam with columns of lower and upper stories fixed at the far end. Cross-sectional dimension of beams and columns may be chosen that moment of inertia of beam is 1.5 to 2 times that of the column, and find distribution factor at a joint considering stiffness of beams and columns. Calculate dead load, live load on the beam. Live load should be placed in such a way that causes worst effect at the section considered, that is alternate and adjacent loading should be adopted. Find the initial fixed end moment and analyze this frame by moment distribution method. Finally, draw the shear force and bending moment diagram. So in this method, sway of the substitute frame is ignored. So you are not considering the sway effect. So for you analyze for gravity load, then do a separate sway analysis for the frame, which is very difficult to do as it is a very big frame, right? So they have given a full analyzed problem in which the floor slab is given, live load, floor finish, beam size, column size, as been mentioned, and a typical floor has been taken with floor heights. They have estimated live load on the beam, dead load, floor finish. This is to be estimated how I explained to you. Okay. Now this is eye of the column, this is eye of the beam, that you have to select eye of the column and eye of the beam. Orientation of the column, you have to select how it is placed. So for that, I had made a frame for you in ETABS. So this is a square column I have considered right now. So either you can take this or you can also update this column sizes in the software, or decide accordingly what is the column orientation and what is the size of the columns or the beams. So you basically need the stiffness for which the assumption of the sizes is necessary. Now in this case, how will you do the initial sizing? So if I go by initial sizing, what you can do is initial sizing of beams and columns. So for gravity loads, now when you go to beam reaction method, right? In beam reaction method, you can get the, SFD with BMD for beam. Okay. So from that, you can estimate beam size. Right. So you can estimate beam size from that particular forces for the beams. Now same when you get the force in the columns, estimate column sizes also. So that is the benefit of beam reaction method. At least from the reactions, you can estimate the initial beam and column size. Otherwise, you can assume, but how many times you will assume, that will become a problem. So in that case, another method is by using the thumb rule. Sometimes people a thumb rule, or they create their own thumb rule based on the practice they have already considered last problems. And from that, you can estimate, let's say for beam, so length divided by 12. Okay, you can take the depth of beam. Okay, or it sometimes becomes L by 10 also. Now for column, how will you estimate the initial size of the column? So any thumb rule for that? So you can take the from
ductile codes are like B by D should not be greater than 0.45. Width we can take equal to beam width.
rather, I would say play with the stiffness. You have got B by D of the beam, increase 1.2 times or 1.1 times for the column for initial case. That way. So that is the TI. So either you play with the stiffness, or you can also use a ductile detailing code in which the B by D ratio is given for the elements. Okay, so type 1, type 2, and type 3. This is the 3 ways you can estimate the initial sizes. Okay. And however, this will never change. Now L by 12 also will depend upon the length. So based on length, you are playing in this zone. However, if you are going by beam reaction method, then it is easy to estimate the initial beam size also. Okay. So you can create your own charts, you can create your own tables, and past practice what you have done. You can solve few examples and put it in a chart for your initial estimation for beams columns. Right. Okay. So this was regarding the gravity loads. So I'll open again this particular literature. So once you get the eye of the column, you get eye of the beam. Now you write the joint, right? In moment distribution method, you write the joint. What are the member AB? For joint B, that is AB and BC. And let's say above member is B1, BB2, that way. So this is AA1, AA2, top and bottom columns, and AB is the beam. Now you give relative stiffness I by L or I by H, depends on that. And for each element at joint A, joint B, joint C, joint D, all joints, all members connected, I by L. Now you total the stiffness. Okay. Now give the distribution factor for the 3 members that are connected at A, 4 members connected at B, 4 at C, D, E. Once you get this, the moment distribution factor, then you are having those maximum sagging moment at center of BC. Okay. What is this case? Is W max 1.5 dead load plus live load, and W minimum is dead load. That is the service case. So serviceability case and strength case, 2 moments are estimated here. and this is a UDL applied. Now there is no point load here. You can also choose based on the particular case. If the moment is roundabout same on two sides, here it is different. Now from where these moments have come, that we have to see. Now this is a fixed end moment you will take, right? WL square by 12 or fixed end moments. Now M of AB, fixed end moment at A is 0, fixed end moment at B is WL square by 12. So W is 15.90, that is only dead load, into L square by 12. Then MBC, again WL square by 12, L square by 12. At E and A, the fixed end moment is 0. Now I will take the joint distribution factor that we had estimated. Fixed end moment is only in AB because the load is at AB. So fixed end moment is only at AB because A is pinned. So it will not have A1, AA2 will be 0 fixed end moment. Only at AB because BA member has a fixity. This we will have a fixed end moment here. Now this total moment will be distributed in 3 members. So that is 6.02, 6.02, 9.16. The first distribution. Now carry over half, you will give it to BA. Okay, from AB to BA, you will transfer half. From BA, you will give half to AB. Okay. Now this 7.12, the sign has changed while transfer, the sign does not change, right? So where does it change? Fixed end moment was negative, distribution is positive, transfer is positive. Now from positive, again when you distribute, it becomes negative. Same distribution factor, and transfer negative. Okay, here it is negative, here it is positive. So from positive to negative, from negative to positive when you distribute it. And finally, in member AA1, AA2, it is 3.98, 3.98, and AB it is minus of 7.96. So 3 members, you got the bending moment. 4 members of B, you got the bending moment. I hope you are getting, and moment distribution method is a routine practice, so I am not going into depth. So if you have doubt, you can ask me. Okay. So fixed end moment distribution, carry over, again distribution, carry over, again distribution, carry over, till you reach to the same answer. 7.96 should come 2 times. That is the length we go in the moment distribution method. So they have done 3 iterations. 1, 2, 3. 3 times distribution. Now, once you get the moments in all the members of a floor in a substitute frame, that is for the maximum case of maximum sagging bending moment. So you have to create that load case of maximum sagging, apply the loads, do the moment distribution method, get the moment in all members. And second case is maximum hogging moment at D in beam, and maximum axial force in column at D. So it is at D, but it can be also C, it can be B, all those things you have to estimate. So maximum force is going to be in this zone. That's why they have taken only one column to estimate the size. Okay. As such, you have to do it for all columns, but this is the maximum case. Again, fixed end moment they have estimated and put it in the table, did the distribution, and found out the forces in all elements in the substitute frame in a floor. Now the distribution factor of the upper column and lower column is same. Therefore, several steps in moment distribution methods are common to both at a joint. So if it is joint C, D, and E, at C it is CD, D it is DC and DE. So this is the joint D in which it is member is CD, DC, and DE. That way it has been mentioned. And E is equals to ED. And for C, it is equals to CD. That is what they have considered. As such, one more number is this. Now, reaction due to UDL, reaction due to moment. So what is CD? CD is this particular case, minus 67. And it is total is 40, 50, 60. So CD is equals to 99 and reaction due to UDL. Okay, UDL is separate, reaction due to moment. So you need to give total of this. So 42.79 plus 12.55 plus 12.55. So that is equal to as such they are neutralizing each other. Now from CD they have written as moment due to reaction due to moment is minus of 3.16. This was plus 3.16 minus plus 9.29. I think there is some iteration done in between. You just have to transfer the moments from for all the joints, okay, and you have to get the reaction at D. So what is the reaction due to the moment and what is the reaction due to UDL? You have to total it to get the reaction on the column. So that I had shown in the sketch to you that whatever force is coming on the column, you have to take it. So this is the point load coming onto the column. So due to the moment and due to the reaction. So this is the total force that will act on the column point load at joint D. So you have to convert the moment into reactions, and also what is the gravity load coming, that is also you have to take. So reactions due to the moment and reactions due to the UDL, both are to be converted to a reaction force. So maximum moment at support D is 83.66, which is written here, 83.66. And DE is 81.37. This one, 83.66, 81.37. Negative and positive. And actual load in column is also at support D, which is 200.55. So maximum moment and maximum load has to be estimated for the column joint. Now minimum moment at center of BC. Third case, maximum moment, now minimum moment. You have to consider that load case where the minimum moment was estimated. The rest procedure is the same. Yeah. So what load cases have to be created to solve the problem have been mentioned herein. depth. This is the same has to be followed for all the cases. Using substitute frame method and moment distribution method. We see the other method that is mentioned. The portal frame also they have given, same has to be followed. The cantilever method is used for tall buildings which are more flexible, that have a cantilever action. In that case, we have to use cantilever method. So this is also there, but I don't think we should go into depth of this. So the method that we have discussed, you should use that as a routine procedure. So I hope you will solve that particular problem for gravity load first. For lateral loads, whatever the shear wall position is there, what is the force coming onto that wall, you have to estimate that we have done already in the last session. And force distribution on the frame, force distribution on the shear wall or lateral forces when the case of shear wall will come. But first target is you should estimate the gravity loads correctly and compare it with the software. So that is the task for this particular week. And the same problem that I have shared, you can use it or you can create your own problem. Right. So any query in what we have discussed today? This was a routine procedure. So I just wanted to know, have you gone through this procedure like I have discussed or not previously? Hello.
Yes, sir. Actually, sir, I got the I get clear things. I will practice that problem that you have shown. I will practice on that.
Yeah, I mean, it is the routine procedure. So are you using it the same way or in a different way? That was the question.
Same way, sir, only. Same way.
Same way. Yeah, so I think it is routine and we can you can estimate the loads in with the two-way, one-way distribution. That is up to you how you do it. Right. So a two-way slab is there. You can convert all slabs to the one-way by introducing the secondary beams. So in that particular case, the two-way action will get eliminated. All beams will be one-way action only. Okay. So that is how also if a span is like 5 meter by 6 meter, on 6 meter, if you introduce two beams, it will be 5 meter of the beam in one direction, but other direction, it will be a smaller size of the slab. So one-way action will take place into it. So that exercise also can be done by you by introducing secondary beams and reducing the two-way action to one-way action. Okay, so I would expect you to at least show some calculation for one single portal frame and compare the reactions of that portal frame from the software. Or we can do it in the software later. You can compare it only with the means you can just estimate for one central frame what is going to be the load and the reactions. The SFD, BMD, and the reactions for that. So beam reaction method, substitute frame method, moment distribution method has to be used for this particular case.
Yes.
Okay. Okay, then we'll connect live next week, but in between, I'll keep asking you that how much progress is achieved.
Okay. Thank you, sir.
Okay. Yeah.
Thank you, sir.
Yeah, bye.